Hi folks, hopefully that first video went well. I'm going to do another problem from WebAssign 5.6. I'm going to do problem 13, one of these many problems that has quite a bit of different parameters involved. So let's take a look at 13 here. So 13 has to do with this thing called the Gompertz growth curve. This has to do with biological growth where there's some sort of restriction in place after a certain point. One example I was able to find online what had to do with tumor growth, actually. And there's some videos out there if you're more interested in what this particular application is. So like many of the problems here, they've asked us about when this function increases or decreases. I've probably already given you a hint that it's a growth curve. We would assume that it's going to be an increasing function and have a positive first derivative. But let's see if we can show that algebraically here. We're taking a look at our function here. So let's see. Let's switch over to my whiteboard here. Okay, so the equation here is a little bit burly. We have an exponential function, c, e, and the whole rest of this is up in the exponent. So we have negative a, e to the negative kt, all as part of our exponent here. So yeah, we have an exponential function within the exponent of another exponential function. It means our derivatives are going to be a little bit complicated here, but no worries. I think we can do this. One important thing to note here is that a, c, and k are all positive constants, so we can use constant multiple rules on them for some of the differentiation that we're going to have to do here. So part A asks us when this function is increasing or decreasing, and so that will be determined by q prime of t. Right, the derivative, and we're looking to see when that's positive and when it's negative. So we just have to be really careful here. I think what I'm going to do for this problem, because we have such a complicated exponent here, I'm going to say the following. I'm going to say that our function q of t is in the form c times e to the u. We're going to call that entire exponent up there just u, right? So in this case, u would be negative a e to the negative kt. Okay, that's just going to help us stay organized. You're going to see that we take this technique quite a bit in the next chapter as well if we have something that we need to keep track of and we don't want a ton of variables floating around the whole time. So u is just going to be a placeholder for this expression right here. And then q prime of t, well, really what we're doing then is we're taking the derivative with respect to time of c e to the u. So we're making that problem a little bit easier by abstracting that exponent to just be u. Okay, so what is the derivative of c times e to the u? Well, by the constant multiple rule, we have a c, right, that stays out in front. And then the derivative with respect to time of e to the u is going to be e to the u times u prime. That is times du dt. So the derivative of u with respect to time. So this is the whole reason why I took this organizing step here to let u equal negative a e to the negative kt, because finding this derivative here, that's going to take us a step or two. In the past, we've done the chain rule just in one step because the chain rule has literally been just multiplying by the number -2 or -3 or something like that. So over here on the side, let me find what u prime is going to equal here. So if u is negative a e to the negative kt, differentiating with respect to time, our derivative then will be negative a by constant multiple rule times e to the negative kt, right? The derivative of an exponential is itself, except finally by the chain rule, we're going to need to multiply by the derivative of our exponent here. So the derivative of negative kt, which, remembering that k is a constant and t is a variable, negative kt's derivative will just be negative k. So let me just organize that a little bit here. So we have a negative a times a negative k, so that will be a positive a k times e to the negative kt. Okay, so now let's assemble what we have here. So q prime of t. So q prime of t is c times e to the u. Well, what's u? U was this expression we made up here. So negative a e to the negative kt. All right, so there is my c. Here is my e to the u. And then last thing for me is my u prime, and my u prime is a k e to the negative kt. Now that is a mess, right? But let's not lose track of the structure that we have here. We have two things. We have two powers of e, right? Here's a power of e. Here's another power of e. And then here are the parameters c, a, and k. Those are all being multiplied together. So I can simplify this in a couple ways. I can take all those parameters, those constants c, a, and k, and just write them at the beginning, right? It's a whole bunch of multiplication, so the order doesn't matter. So I have a c times an a times a k. And then to the power of e, here's what we have. We have e to the negative a e to the negative kt, right? That's from our first part here. We had another power of e that's just to the negative kt. Well, one thing we know about exponential expressions, if we have two exponential expressions and we multiply them together, we're allowed to just add the exponents. And so the multiplication of those two powers of e, all I can do is add the exponent negative ae to the negative kt. I'll add that to negative kt. So it's minus kt. Okay, so there's our first derivative. And it still looks like a mess, but remember what we really need to do here. We need to determine if the function is increasing or decreasing. Well, again, let's look at these one piece at a time. We've been told that c is positive. We've been told that a is positive. We've been told that k is positive. And then even though this power of e has a really complicated looking exponent here, we know that any power of e has to be positive. Doesn't matter what's going on up there in the exponent, any power of e will be positive. And so without even delving too deeply into the exponent here, we can conclude that our first derivative has to always be positive, or to write that another way, it's always greater than 0. And so what that tells us is our original function q of t is always increasing. That's good. We were told it's a growth function, so the fact that it's increasing shouldn't surprise us. I think in a problem like this, the calculus really isn't that bad. There was a chain rule within a chain rule problem, so that can get kind of complicated. The strategy that I use to make that a little bit easier is to say, okay, I have q of t equals c times e to some mess. Let me call that mess u, just temporarily, so I don't have to look at all those letters at the same time. I wrote it at c e to the u, took the derivative using the chain rule, and then what I needed to find was e to the u and u prime. And I did the u prime over here on the side, so it wasn't too many things at one time. And then all I had to do to finish my problem here was assemble the answer. So here we have part A. I'll come back in a moment and we'll see if we can do part B. Hi folks, we're going to continue with problem 13 on WebAssign 5.6 on the Gompertz growth curve. Part A, we found the derivative to determine that the function is always increasing. Part B, they've asked us to find the time at which the growth rate q prime of t is increasing most rapidly. Now, one way to do this that would probably be the harder way to do this would be to look at the first derivative and try to find the absolute maximum of that function. And that would require taking a derivative and then also using a first or second derivative test on that first derivative. Be kind of time consuming. So one thing we can do, they're kind of nice, they give us a little hint here to find the inflection point of the curve. Right, the inflection point is going to be the place not only where the curve changes concavity, but locally the steepest part of the curve. So that'll be a little bit easier. It'll mimic a lot of the same steps if we did it another way as well. So let's go back to the whiteboard here. I copied our results from part A, specifically our derivative here. That was from part A. This is why this is sometimes known as the cake problem. If we write out that first derivative, it does spell out cake. So what we're trying to do now is we're trying to figure out what the inflection points might be for this curve. So to do that, we'll need q double prime, and q double prime will be a little bit complicated. That's not super bad in that it's going to use the exact same technique that we used to find q prime. I'm going to temporarily say, all right, well, q prime of t is kind of like a complicated looking function, so let me just simplify it by saying it's going to be CAK times e to the u. And in this case, u would be negative a e to the negative kt minus kt. Right, that's what's standing in for our variable here. Just we don't have to write it a bunch of times. And so we can be more organized in our thoughts when we start taking derivatives. So q double prime, the derivative of q prime, by the constant multiple rule, we'll have c, a, and k all as positive constants. Those can be factored out. Our derivative of e to the u will be e to the u times u prime. Well, I know what e to the u is. E to the u is this beautiful thing right here. So our second derivative is going to start by writing the exact same thing that we had here. And then the only difference is we're going to have to multiply by u prime. So let's figure out what u prime is based on u being designated as negative a e to the negative kt minus kt. Okay, well, let's see, u prime. U prime, if we just go term by term here, we have negative a as a constant multiple. We have e to the negative kt. Okay, so again, taking the derivative of e to the negative kt, it's going to be itself times the derivative of negative kt, which is negative k. And now this minus kt, k again is a positive constant, so the derivative of negative kt is going to be negative k, right? We're just dropping down that power of t from 1 to 0. So here's our expression for u prime. And now we're ready to write out q double prime. Q double prime, it's going to be pretty. Q double prime of t. So we have c, a, k times e to the u. And I'm going to write the actual expression for u just like I did in the original. So negative a e to the negative kt minus kt. Okay, so there's our c, a, k, e to the u. And then finally multiply by u prime. So this whole expression here is then going to be multiplied by negative a e to the negative kt times negative k minus k. Okay, so we want to find some inflection points. We want to know when this thing equals 0. I'm going to do a little bit of cleaning up again, really just in my term right here. Maybe I'm actually going to do it via erasure. You see back here, I have a negative a and a negative k. You multiply negative a and negative k, that's just going to give us positive a k, right? Negative a times negative k is positive a k times e to the negative kt. Just a couple fewer things for us to keep track of. And we want to find inflection points, so we want to know when this whole thing equals 0. And one thing to consider, c will never be 0, right? C is positive, a is positive, k is positive. E to some power cannot possibly be 0. This whole expression here cannot equal 0, right? We want our second derivative to equal 0 if we're looking for inflection points, so it can't happen here. It must happen from somewhere else in the equation. So what's left over is this ak times e to the negative kt minus k. And so we should ask ourselves, could this possibly equal 0? Well, for that to be true, what would have to happen is that a times k times e to the negative kt would have to equal k, right? If those two things were equal, then their difference would equal 0. And we want this to equal 0 if we're looking for inflection points. Okay, so let's see if we can make this happen. Can we make a k e to the negative kt equal k? Well, I have a factor of k on both sides. I could divide that out, right? If I do that, I have a e to the negative kt equals 1. I'm running a little short on space here. I'm going to bring it back up here so we don't run off the page. Okay, so in order for that to happen, we would have to have e to the negative kt equal 1 over a if we divide both sides by a. So e to the negative kt equals 1 over a. And now remember, our only variable here, our independent variable, is t. So we're trying to solve this equation for t. In order to do that, let me take the natural log of both sides. So the natural log of e to the negative kt should equal the natural log of 1 over a. And if we take the natural log of e to some power, well, e to some power. If we take the natural log, those are inverse functions. We'll be left with negative kt equals the natural log of 1 over a. And finally, to solve this for t, we have t equals the natural log of 1 over a divided by negative k. Bring that up here a little bit so you can see it. There we go. So here is our possible inflection point. And we're interested, if we want to call it an inflection point, we actually have to show that it changes concavity from one side to the other. That's pretty, should be not be bad for us to do. Taking a look at what happens to our expression here. If we increase t by a small amount, well, then this expression will become smaller, right? It's an exponential decay curve. So if we increase t by a little bit, this will become smaller. As a result, this ak e to the negative kt will be a little bit less than k. And so when we subtract right in here, we'll get a negative number. Whereas if we take the value of t a little bit smaller, what we know that will happen, because it's an exponential decay curve here, is that this expression will be a little bit larger, and ak e to the negative kt will be slightly more than k, giving this entire factor here positive sign. So we will have a change in concavity. This is the inflection point, and here's your answer to part B. Now, one thing you know from our previous work with logarithms is sometimes there's more than one way to write an answer here. So for example, this natural log of 1 over a, one way that we could simplify that, 1 over a is a to the negative first power. So you might also see an answer written like this. If we think of that as a to the negative first power, we could take that a out in front, and you might have as an equivalent answer t equals just the natural log of a over positive k. So again, you may find slightly different ways to write this answer here, but either one of these should be fine for WebAssign. Okay, folks, so we're going to finish problem 13 here. We've determined that the function is always increasing. We found an inflection point at natural log of a divided by k. And the last part asks us to take the limit of our function q as t approaches infinity. So as it turns out, that's probably going to be the easiest of the different parts here. And just like we've done with some previous problems, let's try and build up our function, just taking it one piece at a time. So my variable t is headed to infinity, so I'll write that first here. So t is going to infinity. Looking outward, the next thing I encounter is negative kt. Okay, remembering that k is a positive constant. If we take t, which is going to infinity, and multiply it by negative kt, that quantity should approach negative infinity. Okay, so we've gone from t to negative kt. Next, we'll go to e to the negative kt. Right, I'm just building outward here from our variable t. So e to the negative kt, remember negative kt is headed to negative infinity. So what happens to e to some power as that power approaches negative infinity? Well, e to a power approaching negative infinity is 0, right? We can think of that as just moving along an exponential growth curve, right? If we imagine y equals e to the x, we know what that graph looks like. Right? It looks like this, exponential growth. If we take the limit as the exponent goes to negative infinity, that'd be taking the limit as we move to the left, right? As x approaches negative infinity. Okay, so e to the negative kt, I apologize, it's a little bit hard to see that. E to the negative kt approaches 0. Okay, so now we've gone this far, we have this much of our function. Okay, so let's look at this whole exponent of e. That whole exponent is negative a times e to the negative kt. Well, we just decided that e to the negative kt is headed to 0, so multiplying by negative a is not going to change that. Take something that's 0, multiply it by negative a, it still equals 0. And we're getting closer now. So now we have the entire exponent of e in the function, right? We know what this whole piece up here is doing. This whole piece up here is headed to 0. Okay, well then e raised to the negative a e to the negative kt, right? That's just e raised to our previous result. E to the 0th power would be 1, right? What we're saying is we just figured out that that whole exponent up here is headed to 0, so e to a power approaching 0 will approach 1. And then last piece here, we now have the entire exponential, including e, right? So we figured out that this whole thing minus the c, this whole part here, that is going to approach the number 1. And so if we have something approaching 1 multiplied by c, then we've actually figured out that our function as a whole should equal, or the limit of our function should equal 1 times c. And so the limit of our function q of t, as t approaches infinity, is c. Okay. I mentioned at the beginning of the problem that this is a growth equation that models biological growth with some sort of limitation. There are probably some population models that would follow this. I mentioned the growth of a tumor. It does make sense in these cases that there would be some restriction on the growth. And so what we've really determined in part C of the problem is that there's a horizontal asymptote to the size of whatever is being modeled using this function. C is a horizontal asymptote and also the limit as t approaches infinity. So let's take a look back at our answers here and make sure we have everything good. Okay, so we have here problem 13. I put in our increasing behavior. I put in our limit, or sorry, our inflection point where the growth rate is increasing most rapidly. And then we've determined that the limit of q of t as t approaches infinity is c. You guys probably know to do this. It took me a minute. I thought we made a mistake on part B because I had a capital K instead of a lowercase k. Just make sure that they match what we have in the problem here. And slowly but surely, this should allow us to determine if that's the right answer. Okay, I won't make you guys wait for that. Hopefully this is helpful. And I'll see if I can do a couple more problems before this is due. Success. Awesome.